Great, no problem. Welcome everyone. This is the first tutorial for dynamics. My name is Matt or Matthew, and let's get started. Let's see, go ahead, okay. Want to introduce yourself, Akib?
Yeah, sure. Hi everyone. I'm Akib. I'm a PhD student in Professor Filters Lab, and my research area is two-dimensional materials. I will be one of the TAs for this tutorial course for you guys with the dynamics, and hopefully we'll enjoy our semester. Yep, with you.
And as I said, my name is Matthew. You can call me Matt. I'm a master's student with Professor Sullivan. He might teach you guys. I'm not sure how the sections work. My research area is aerodynamics or turbulence, so fluid mechanics, and both of our emails are there if you want to reach us. So let's get started with problem one. It's there for you guys. I think Akib also provided it in the chat if you want to download it from there. We'll give you, 7 to 10 minutes or so to work on it, and then we'll come back and solve it together. If you have any questions, you can post in the chat or speak up.
Ne oldu? Abo.
Hi.
İzlemiyor musun
Yeah,
lan
go ahead.
maçı? Ha. Bu ne lan? Mekanik soru.
Hangi ders?
Dynamics. Oh, my bad. My mic was open.
No problem.
Is the left hand the pole face or the right hand the pole face?
Sorry?
The right end is the pole face.
Thank
No problem. The final answer is based on K and L. X shouldn't be in there. So you get an expression for V as a function of K, L, and X, and then you sub in X as a function of L and K to get the final answer. So yeah, you have to be careful with what X is because the diameter of the ball has to be subtracted, or half the diameter. So I mean, I'll cover that in the solution, but X isn't just L. Yeah, hint. I'll cover the solution in about 2 minutes. So just so you guys know. Okay, let's get started on the solution. So to begin, if you guys have any questions while I'm covering it, feel free to jump in or post in the chat. If you want to cover anything again, let me know. Yeah, let's get started. So we start with the equation relating velocity, displacement, and acceleration. So v dv equals a dx. Then we integrate. So our limits here 0 to v, and for dx it's 0 to x. We substitute the known relation from the question, acceleration equals k over l minus x squared. Then we perform our integration. So yeah, I mean, if you want me to cover the how the integration goes, let me know. So that's the next step. And then you solve for v. So isolate v of x. That's that covered there. And then, yeah, as people were talking about in the chat, to be careful here, x equals L minus d over 2. Based on how how the problem was laid out, x isn't just L. You have to be careful. You have to subtract the radius of the ball. And we substitute that x into the expression we found to solve for v. And so there's the final answer. X in the numerator as well. Okay. Great. If anyone has any See upper bound for add. Okay, a couple questions here. Is the upper bound for? Yeah, the upper bound for the right side integral is x. We've used b squared.
Wait. Why is the 2 outside of the square root at the end? For v equals 2 root.
Yeah, 1 sec. Let me just see x equals. I'd have to do this solution. I don't have it on hand, but I think it comes from simplification. Do you want me to cover the simplification?
No, I think that's good. It's okay. It's just like arithmetic, right?
Yeah, I think when you substitute x equals L minus d over 2 in the bottom, the 2 becomes a 4. There's like a factor of 2. So they just brought the 2 out.
Yeah, I think I see.
Okay. Where do we use it? Oh. So in the upper bound of a dx is, so we just use x because, or you can't use L because, let's go back. It's not like you have to factor in the fact that there's the radius of the ball. It's not just as simple as using L. Are there any remaining questions? I'm not sure if I've answered all the ones in the chat. Previous elements. I believe so. I haven't tried that myself, but I think that would work. Maybe give it a try and or maybe when you guys are solving the next problem, I can give it a try and I'll let you know. Any remaining questions before problem 2? Or anything you want to add, Keith?
No, I think you're good. Fine.
Okay. Okay, let's move on. Problem 2, we got a freighter moving at 4 meters per second. After the engines are shut off, decelerate the proportion of the square root of velocity, or its square velocity. And after 10 minutes, the speed is reduced to 2 meters per second. So the goal is to find the distance traveled in those 10 minutes, and the speed is a function of the time. So there's 2 solutions we're looking for in this problem. I'll give you guys about 10 minutes. Okay, that was about 10 minutes. So let's get started on the solution. Again, if you have any questions, just post them in the chat. So to start, sort of similar to last time, we just start with the simple equation for acceleration. And we use this to get our general form for the velocity equation. So as you know, A equals dv over dt. And from the question, we have that equal to negative kv squared. We rearranged to get this into a form with velocity along with the dv, and then dt along with k. And we integrate. After that integration, we have a general form for the velocity equation as a function of t and these two constants, k and c. These constants aren't known, so we have to use boundary or initial conditions from the problem to get them. So that's the next step. From the problem, we know that the velocity at time 0 is 4 meters per second, and the velocity at 10 minutes, so 10 times 60 seconds, is 2 meters per second. Using these two boundary conditions, we can use those to determine the constants c and k. So first, we use velocity at time 0 is 4, and then sub in 0 in the equation, and solve for c. We get c is 1 over 4. And then the second boundary condition, velocity at t equals 600 seconds is equal to 2. We sub in t is 600 and c from the previous part, 1 over 4. We solve for k. We get k is 1 over 2400. And then finally, we sub in the constants to get the velocity as a function of time. This is our final answer for the first part, plus c in the denominator. This will be something, depending on how you set up the equation, your c will be different, but you'll work out to the same answer in the end if you've done it right. Is t, I think as a general rule of thumb, you should keep t in seconds just to keep units consistent throughout the problem. If you've done it with minutes and it worked out fine, that could work. I didn't try it that way myself. I think in general, it's a pretty good rule of thumb to keep t in seconds, just because if you're working with meters per second, you want to keep your units as seconds. And sorry, I don't think I fully answered the previous question. The way you do this integral and how you have the c in the end, it may vary. You can have the plus c externally. I think it should. I'm not sure if it'll work out the same, but it's likely that you can do it that way and still end up with the right answer. It'll just be a different c. What really matters is if the equation at the end is the same. Anyway, so final answer is v of t is equal to this format, or if you simplify that down, it's 2400 over t plus 600. Any other questions for part 1?
How did you evaluate the integral, the second integral equation?
Okay.
Or how did you get between? Could you
Yeah.
talk about that?
Sure, I'll try to cover that. So I think for future tutorials, I'll work out these intermediate steps. I've sort of skipped them in the solution, but just to clear up any confusion in the future, I'll try to work out the intermediate steps. The first line, yeah. So let's see. I think the right side integral is pretty self-explanatory. That's just negative kt.
Sorry, I meant like how you got from like, sorry, not evaluating it. I mean like how you got from the left side differential, like a is equal to v over dt, how you got the integral equation.
Okay, sure. So we have a equals dv over dt. It's a pretty well-known equation. And from the problem, we have that equal to negative kv squared. Now, knowing that relation, we ignore the a, and we just work with dv over dt equals negative kv squared. And in order to put this into, to get to this integral, we want to put the terms for that associated differential on the same side. So we bring this v squared over to the left and the dt over to the right. This is basically just solving a differential equation, which gives us 1 over v squared is equal to negative k dt. And then we just integrate both sides. Does that clear that up, or is there still
Yeah.
confusion?
Yeah, that's good.
Okay. And then from there, Miguel, solving the integral of 1 over v squared is negative 1 over v. And then the integral of negative k dt is negative kt. Since they're both indefinite integrals, we have to add a constant. Technically, you should add a constant to both sides, but it works out the same if you just add a single constant. And then we just solve for v. If you'd like to cover how to solve for v, I could do that. That's just algebra from there.
Mhm.
We have any other questions for part 1? Okay, let's go on to the second part. So the second part, we need to solve for the displacement, the total displacement traveled in that 10-minute period. So again, we start with the general form for velocity and displacement, that equation. So v equals ds over dt is how we start. Sort of similar to the last time. We want to rearrange such that we have these differentials on opposite sides so that we can do the integration. We have this equation for v, 2400 over t plus 600 from the previous slide. And then on the left side is just ds. From there, we solve the integral to get this general form for displacement, s equals 2400 times log of t plus 600, and we have our constant. It's important to remember that. Again, we don't know this constant, so we have to use our boundary conditions to determine it. So from the problem, we know the displacement at time 0 is equal to 0. That's how we'll define it. Using this boundary condition, we can solve for c. So we substitute displacement at time equals 0 is equal to 0. So 0 equals 2400 times log of 0 plus 600. And if we solve for c, we get negative 15,352. Now that we know c, we can solve for the displacement after 10 minutes. So displacement at t equals 600 seconds. So I'm using seconds here to make sure the units are consistent. So t600 is equal to 2400 times ln of 600 seconds plus 600 minus RC, which is negative 15,000. And that equals 600 or 1663 meters. And that is the solution. Do we have any questions before we move on? In the classroom, I would probably be writing on a board, I assume, which might help show all the steps more clearly. For the next tutorial, I'll try to write out the steps so we're not skipping over the algebra, because I know that can be a little bit confusing. So I'll keep that in mind. Before we move on to problem 3, I just wanted to mention for Jingmin, you had asked a question about problem 1. You can use L minus D over 2 as the upper bound for ADX. I solved it for while you guys were solving problem 2. It does work out the same, so that also works. The reason you use X as the upper bound is it just simplifies the integration, and then you sub in x after you've got the general solution. It should just simplifies things a little bit, but both ways work. Okay, if we have no questions, I guess Keep can take over. I'll stop sharing and you can share your stuff.
Sure. Awesome. Thank you, Matthew.
No problem.
Just let me share my screen. Could you please give me the access to my another account as well? I'm just logging from the tab.
Sorry, I have
Akib.
to.
It says Akib.
Okay.
AKIB.
Yeah, I will do that.
Thanks,
Should
appreciate
be.
it. Yep,
okay.
it's fine. Thanks, appreciate it. Okay. Okay, folks. Then we'll move on to problem 3. The problem 3 will be on the projectiles. So the problem is very simple as well. Let me try to draw. Okay. So you have this marksman. Just give me a second. Oh, come on. Okay. So you have this marksman who is shooting a rifle to a target which is at 1500 meters far from himself. The taking point of this problem is the rifle's nozzle here is aligned with the center of the target, okay? And he's shooting at a 900 meter per second. So you need to find out what would be the angle of launching for both cases so that it at least hits the target. So let me just simplify it for you. How can it at least hit the target? For example, this is your target, right? Let's say this is 160 millimeter, right? And your nozzle, let me draw it down so that it's very clear. Okay, let's say this is your target. This is 160 millimeters, and your rifle's nozzle is somewhere here at the center, right? Now, you can have two different kind of projectile motion or two different extremes. You can either hit the top of the target or the bottom of the target and anything in between, right? So the two extremes are top and bottom. So if you launch this, then probably it'll hit like this. And if you launch this, it'll hit like something like this, right? So if you can find out what is the angle to hit the top and bottom, and in between all of them will be your launching angle that can hit the target, okay? So the question is actually asking you to find this range of angles so that you can at least hit the target, okay? And you are not expected to calculate the aerodynamic drag, which makes the sample problem a lot easier. I'll give you guys 10 minutes. You need to use the projectile motion equations both in X and Y axis. So yeah, now it's 12:51. I will come back at 1 p.m. Okay. In the meantime, if you have any problem in understanding the question, please put it in the chat box. I'll answer, or you can unmute yourself and ask whatever you prefer. Okay, I believe you guys had a chance to solve this problem. Let's see. Okay. I've broken this problem into a few steps so that I can explain it to you guys easily. Let's see. First of all, we are going to use change the color. Okay. Yeah, we are going to use the projectile motion equations for this problem. Okay, and whenever you have a projectile that is going at an angle, something from horizontal, that's theta or something like that, whatever it is, you should always try to divide them into two components. The horizontal components as the x component and the vertical components as the y component, right? And you know the equations for the projectile motions. First of all, if it is the constant velocity in any x direction, you don't consider the acceleration, whether it's gravity, whether it's an enforced acceleration from the outside, whatever it is. For example, if you throw the projectile in this direction at an angle theta from the horizontal axis, you don't have any acceleration in the x direction, right? So you can write the velocity equation as x is equal to x naught plus v of x naught times t, where x is the final position and x naught was the initial position, right? V of x naught is the component of the velocity that is in the x direction. Usually it is the cos theta component, right? V cos theta. So V of x naught is actually V cos theta, and V of y naught is usually V sin theta, right? And you know whatever time it is. But when you are considering the y motion, this one, right? Then you have an acceleration or deceleration naturally occurring, that is the gravity, right? And the gravity is acting downwards. So it is important to set up your set of coordinates. For example, for this problem, I have set this x as positive, this y as negative, right? So our gravity is negative since it is acting downwards, right? Up to this point, if you have any questions, please feel free to unmute yourself or ask questions, whatever you prefer. So if you have if you have a gravity working on your projectile, you can use this equation where it takes into account the gravity. Okay, and this is actually not GT. Oh, sorry, it's a PDF. It's V of y naught times t, same as the x, and you can also have the equation relating to different position and the velocity as well. Okay, and as I explained to you before, for this target, you need to hit either the top or the bottom to find out the two extreme maximums, right? So this is the theta, or the angle of the range of angles where you can shoot your projectile so that it can hit anything in between this as well, right? So if it is 0.16 meter, this is half of that, and this is half of that, right? So this is d by 2, and this is also d by 2. So from the center to the top, it's half. From the center to the bottom, it's also half. Okay. Now, bearing in mind, when you are going from the center to the top, it is plus y, and center to the bottom, it is minus y, since we set our coordinate as plus x and plus y. Okay. So let's go back to our problem. Okay. So once you have this velocity, you can divide it into two different components. One of them is your horizontal component, and one of them is your vertical component, right? Now we applied the equation for the projectile motion, that is xb minus xa is equal to v of x naught t, which is nothing but we wrote the equation before, right? X minus x naught is equal to v of x naught times t, or we wrote as x equal to x naught plus v of x naught times t. So xb is your final position, xa is your initial position, and you know the velocity, the magnitude of the velocity at least, right? So the displacement from this position to this position is 1500 meter. From the equation, you know that, right? From the distance from the rifle's nozzle to the target in x direction is 1500 meter, right? And you know the magnitude of the velocity is 900 meter per second. So since it is horizontal component, is cos theta times t, right? Now you can have two different solutions. First of all, you can solve in terms of t, or you can solve in terms of theta, whatever you prefer. It really doesn't change the solution. If you use t, you will have a quadratic equation when you substitute it next time. And if you use theta, you will have a triangular equation when you have the next time, right? I try to prefer the quadratic equation because triangular equations are a little bit hard to solve. But if you want to do it, feel free to do it. It will not change the answer. Okay, so for now we have this relation between theta and t, okay? And we have solved the horizontal component of this velocity for this projectile. Now let's go to the vertical component, okay? We're talking about the bottom of the target. So our y is negative, as I mentioned earlier, right? Since we considered upward is positive, since we are coming to the bottom of the target, this is our negative portion, right? And as I explained to you why it should travel half of the diameter, you know that it's v naught sine theta minus half gt squared. Minus half gt is coming actually, it is plus half minus gt squared. Since gravity is acting downwards and we took our y-axis positive as the upward, it's just minus half gt squared, okay? So now if you substitute the value of t here, you will find from here to in this equation, you will find your time as 1.66 seconds and theta as 0.517 degrees, okay? Now, if you take the same, if you do the exact same thing for top of the target, instead of having negative y, you will just have positive y. And this change of sign will change your value of the degree or the angle, but the time will be the exactly same. So you will find the time is 1.67 second and the theta is 0.524 degree. What do you mean by how did you do the solving? You just jump to answer. You plug in the value of t into this equation. You have the value of t, okay? You plug in into this equation and you will have the solution. You'll have the answer, okay? Well, if you do the triangular equation, you'll have even more ugly equation. Okay. How do you simplify it? What do you mean by, oh, you want me to do the plug-in and then simplify? Okay, okay. I'll try to simplify it and then I'll try to post an answer afterwards, okay? Okay, for now, this is our answer. Like for the bottom of the target, our angle is 0.517 degree, and for the top of the target, it's 0.524 degree. So anything in between should be good range of angle. Okay, okay, I'm stuck in simplification too. Okay, sure, I'll try to solve it and then I'll try to upload it. No worries, that's fine. Do you guys have any question so far with this problem? You have your answer, right? I'll upload the question. I'll upload the answer. Anything else? Sorry, is G 9.8 or minus 9.8? Depending on how you set up your coordinate. Okay, if you set downward is positive, y, you can use 9.8 as positive. But if you set just as I said, upward is positive, then it's minus 9.8. I typically just set up the equation. There is no convention. No, there is no convention. It depends on how you set up your problem. But whatever you set up, you should be consistent throughout the problem. That is the most important thing. Okay. Then I will move on to the next problem, which is a much simpler one. Okay, there's a little correction. This is theta. Okay, let me explain the problem to you. This guy is trying to shoot a basketball, okay? And when he's trying to shoot it, the ball barely clears the hand of this guy. What does it mean by barely clear? That means it just crossed over its hands, right? So you can see, or you can consider, the X and Y coordinate for this basketball is very similar as this guy, wherever he is, okay? And it says that it goes inside the hoop. So if it goes inside the hoop, you have two different coordinates to solve the problem. First of all, the ball is clearing this guy's hand, and then the ball is going inside the hoop, right? So let us try to see what are these coordinates could be. First, let us see what is the initial position. Let's say this is our point of reference, okay? So if it is our point of reference, we can consider X equal to 0 and Y is equal to whatever this height is, that is 2.1 meter, right? Then this is for point A. For point B, since it's barely clearing this guy's hand, we can consider X equal to 7.5 because this guy is standing here, right? And for Y, we do not know. It's 8. We'll have to solve it. For point C, we know that the basketball is going through this hoop, right? So our X is this plus this. That's 7.5 plus 1.5. That is X equal to 9. And Y is equal to this, D. D is 3 meters. So you have 3 different setup points where you can use the projectile motion equations both in X in Y direction, right? Using these 3 points, you should be able to solve this problem. I'll give you guys 10 minutes to do that. It's 1:12, so I'll come back at 1:22. I'm trying to break the problems down as much as I can, but it's really not possible to show you exactly line by line. So my apologies for that. I'll try to be as much discreet as I can. Okay, so let's try to solve the problem. Okay, so as I've explained to you already, that this is the initial position. Let me change the color, something green. This is the initial position that we are trying to consider for this problem. Okay, so anything that we try to measure or the equations that we try to write, this will be a point of reference for the x and y coordinate, right? Now, for this A, we know this both x and y. For B, there is one unknown. For C, we know for both, right? X and y. Let's try to do one thing. Let's try to avoid B for now, since there is one unknown, and try to solve with A and C, because we know the position for the ball at a given point at both locations, right? Let's just say for this portion, for position C, the ball is thrown from point A and is passing through the hoop. Let's say this guy does not exist for us yet. Okay, it's gone. Let's try to apply the projectile motion in x direction, just as we seen before for constant velocity. Since if it is v, it is v cos theta, and this is v sin theta, right? And if you are shooting at an angle theta for our x motion, we can consider that v is constant. Only v in y direction is changing, right? V in y is changing because of gravity, right? Okay, so let's apply this equation. Let's say that it will take time tc for the ball to reach from this point to here, right? And our question asks what is the height of this and also the time. So if we apply the constant velocity equation, this is what we have, right? We know the final position. We know the initial position. The final position is x equal to 9. Initial position is x equal to 0. That's what we have put. We do not know the velocity, VA. Let's consider it VA. Cos 30 degrees, since our theta was 30 degrees, and the time taken will be DC. So from here, you have got one equation, right? Second, you apply the projectile motion in y direction. Again, this is not minus half gt square. This is just plus half minus gt square, right? Because I have taken the upward direction as positive. If you want to set up your coordinate as the downward position as negative, positive, so this is plus y, then you will write plus half gt square. It depends on you, but be consistent with whatever you're writing, okay, or whatever you are assuming. From here, we also note our initial final position and our initial position. We know the equation for the horizontal component and GTC square. So from here, we have another equation, right? So we have one equation here, cos 30. You know the value of cos 30, that's probably root 3 by 2. You know the value of sine 30, that's half. So if you have two equation and two variable, you should be at this point able to solve the equation. And from that, you get the time 0.936 second and velocity 11.102 meter per second. So you know the time to reach from point A to point C, that's this one. And now you know the velocity, that is 11.102 meter per second. But this is not the end of the question. The question also asks you to find this value h, right? Now let's say this hoop is dead for us, okay? We are not considering this hoop at all. Forget about it. Let's consider this. Now, this is our initial position, and this is our final position, right? And for the VA, we already know that our velocity is 11.102 meter per second, right? Okay. I have applied the Y equation first and X second. It really doesn't matter what order you do, just do it perfectly, that should be fine. So if I'm taking Y as positive, again, for these 2 points, A and B, I can write the equation for projectile motion in y direction, very similarly to the previous one. Only this time I'm considering TB as the time to reach D, the right time to reach B. That's it. Very similarly, I can write the projectile motion in x direction. And when I'm writing the projectile motion in x direction, I know the final position. I know the initial position. I know the velocity VA. I just calculated it before. I can easily find out this TB, right? The time to reach B. That's 0.78 seconds. Now, once you know this TB is equal to 0.78 seconds, if you plug in this into this equation, right? You don't have to know H, you know TB, you know TB, you know G, everything is known to you, right? And then your H will come as 3.447 meters. That's it. It's very simple. So whatever equation you guys, whatever problem you guys are given for projectile motions, try to resolve them in both X and Y direction. And from that you can work on. There's a question. Shouldn't the initial position of Y direction be 2.1 rather than 0? Yeah, it should be. That's what I wrote, right? Where did you get Y is for position B? Okay. Oh, yes, sorry. Yes, you're right. It should be 2. Sorry about that. Yeah, perfect. Okay. Any other question? Yeah, it's a 2.1. Sorry, I first solved the problem, then I try to break it down in the tab again. So then the slip of the writing comes. Okay, anyway. Any other question regarding this problem? Can you scroll down real quickly? Yeah, sure, no problem. Let me actually zoom it down. Is it okay? End of seek. Okay, awesome. Any other question? I'm not sure if we can upload the solution yet because the HTA has not told us to do that yet. Once he tells us to upload the solution as well, I will upload. The problems are there already. You'll have the solution as well if they allow it. Scroll up to question 1. Yeah. Yep, no problem. Okay, I'll give you guys another 1 or 2 minutes to ask questions. If you don't ask by then, I will consider there isn't any anymore.
I had a question about
Please.
what is it? Not this particular problem, but
Yep.
like, I guess the idea is in like problem, like questions like problem 2, involving like acceleration as a function of velocity or displacement.
Oh, okay. Okay.
I'm
Matthew?
kind of, I always have trouble figuring out how to put, like, I can't wrap my head around acceleration as a function of velocity or like displacement. Like, do you have any tips for that? With questions like problem 2?
Matthew, you here?
Yeah, I'm here. Sorry. Problem 2.
Yeah.
Yeah, I think in general, I mean, there's a couple sort of general form equations like A equals dv by dt or V equals ds by dt. If you can, I mean, everyone should know that by undergrad. I mean, I'm sure you know those equations. That's often like the starting point for these kinds of questions. From there, a lot of the time, they'll require like an integration of velocity over time gives you your total total displacement and integration of, yeah, I mean, so if you use those principles, like the initial equations for acceleration and velocity, you can get pretty far. And then it's just a matter of knowing how to do some differential equations. I can't remember if you guys have covered any differential equations at this point, but just knowing some of those basics, like how to solve a really basic differential equation, can help a lot in these kinds of problems. Like as I covered in problem 2 specifically.
Because for me,
Is
like,
that
as soon as I get, so like if I'm given like a as a function of s, then I have to find s as a function of t. Like I have difficulty understanding how to do that.
okay? I might have to see a kind of like a question that you're working on to maybe to understand what you're getting at. Like problem 2 gives you acceleration as a function of velocity. And then you can use the relation between acceleration and velocity, like a equals dv over dt, to solve for velocity as a function of time. It's just making that first connection. Like you have acceleration as a function of velocity, and you know you need velocity as a function of time, so you need to find a relation between velocity and time to help you get there. And so using dv by dt can help. I think it's sort of a matter of practicing enough problems to help you get the hang of it.
Okay, I see.
I guess knowing what you want in the end, like you know you want velocity as a function of time, so you have to think about how you get time related to velocity. So you got to think about what equations you know and how to combine them to get to your final form.
Okay, I see. So it's like in the case of acceleration as a function of s, or sorry, as a function of like position,
Yep.
and you wanted to find like position as a function of time, you would use how would you approach that? You would have to use like a is equal to dv of dt, and then v is equal to st of over dt or something, right?
Yeah, and I guess in that case you have a is equal to dv by dt, and you know the second derivative of position is acceleration. So you could go d squared s by dt squared, like the second derivative.
Okay, yeah.
So I mean that's a direct relation. So a equals d squared s by dt squared, the second derivative. So that is a direct relation you could use.
Okay. Just gotta practice it, I guess. Okay, thanks.
Yeah, if you have any specific questions, you can also send an email, I guess, to try to help there.
Okay, someone asked about the memorizing the equations. I think David told that you guys are allowed to have an 8 sheet. I'm not sure. I think professor may have mentioned it in the class. So yeah, there you go. Oh, it's in the syllabus. Okay, perfect. Yeah, you are not supposed to memorize everything when it is on the book, right? At least some basic equations, I think you should have it on top of your head, because when you're trying to solve a problem, it's really difficult to navigate through your small 8 sheet where you can barely read what you're writing, right? So it should be on top of your head. And as I mentioned, the supplemental videos really help. And how you should use the supplemental video, I think the best way to use it, the professor actually explains what sort of problem and what kind of solutions that you should be thinking. So for example, let's say he explains the types of problems, right? So if he says that, okay, this is the projectile motion equations, then immediately you know that you should divide it into the x and y direction. right? If it is a friction problem, you immediately know that you need to divide it between the static friction and the kinetic energy. So he explains it very well in his supplemental videos about these issues. So if you can go through this will really help, because I know it's a tough course, but it is really important for you to look at the problem and immediately know what sort of problem is this. Is it a friction problem? Is it an energy problem? Is it a projectile motion problem? And those videos will help you in that regard. Okay, at least that's my experience from previous years. Okay, so if you guys don't have any other questions, then thank you so much for attending this session. Hopefully we'll post the recording soon as well, and see you next week. Yep, no problem. Thank you.
Thanks for coming, everyone.